Previously, I posted a video about propagation as it relates to ship defense against missile attack. And in that video, I talked about a curved earth propagation model and signal reflections from sea swells on the sea surface. And in the end, it all relates to jog detection, which is the cornerstone of how we know that the jamming is working against the missile. And I would say it's also the cornerstone of cognitive jamming against the missile, which is the future of counter-missile jamming. Now, the earlier video, the propagation video, is basically worthless unless the propagation model is correct. And what I mean by correct is it accurately predicts the RF power levels in the seeker and in the jammer during a real-world combat engagement between a missile and a jammer. So this video is about the evidence that makes me believe that the propagation model I am using is correct. Now, I didn't write all the math in the propagation model, but I wrote some of it, and I coded all of it. So this video will present the results of several experiments that make me believe that the propagation model is correct. Now, I don't have a plane and I don't have a missile seeker, and those data would be classified, almost certainly would be classified anyway, so I can't present anything like that. So all of the evidence that I present here will be indirect, but it is real.
Now, the bit of the background is several years ago, I was interested in and working on countermeasures against radio-controlled roadside bombs, and specifically how we can know that the jammer is working in real time under combat conditions. So it's a similar concept as missile engagement. I did more tests than I can talk about here, just for brevity, but the ones that most convinced me that the propagation model are correct, those are the ones I'll talk about, and there are 5 of them. So in the first test, I compared predicted RF power and measured RF power over a flat asphalt test range at IED radio frequencies of about 900 megahertz. In the second test, I repeated the experiment, but at a part of the test range where there was a gentle dip in the asphalt surface, like it's not flat. Third test, I again repeated the same experiment, but at a part of the test range where the asphalt road was flanked by a chain link fence. Fourth test, I performed measurements at an indoor tennis court where there were a lot of scatterers everywhere, and most of them are invisible. And in the fifth test, which is to me the most interesting one, I put the transmitter on a wooden tower beside the asphalt road and measured the RF power along the length of the road for 3 different positions of the transmitter on the tower deck. Okay, we have to talk about background and the experimental setup because otherwise the rest doesn't mean anything. This project was internally funded, so it was cash poor and equipment poor, and frankly, in my experience, that's when the innovation happens. Roden Schwartz Canada lent me an SMBV 100 vector signal generator, and I bought an FSH4 spectrum analyzer from them. Tektronix Canada lent me a 7122 arbitrary waveform generator, which interestingly was able to run the Protection Range Estimator software. They also lent me an SA2600 spectrum analyzer, beautiful piece of equipment, which literally the day before Marek Skidorva was to hand it to me, it was assigned an ITAR designation, so many thanks to him for the behind-the-scenes work to finally make it happen. And iCore Technologies loaned a Caliber T5 EOD robot for propagation tests. So we're not talking about a couple of measurements here. This is a proper scientific campaign to validate the propagation model. And this is the same propagation model I used in the counter-missile work, so that's the relevance to the earlier video. The operating frequency of these tests was around 900 megahertz, which was chosen because it matched a cordless phone I had at the time, which I also wanted to use as a transmitter. And I had a friend make me a couple of 900 megahertz dipoles from semi-rigid coax. I built 2 collapsible wooden antenna stands, which allowed the coaxial feed cables to be stretched out about 2 meters behind each dipole, which you have to do, or the measurements are contaminated by the cables. The spectrum analyzer was paired with a wireless laptop, which allowed me to record spectra on the laptop. 20 seconds of spectra, let's say. And the test concept was to record about that 20 seconds of spectra at a distance that was incremented, let's say 1 meter at a time. And I could do this for 100 or 180 meters, let's say. That's a lot of measurements, a lot of recorded spectra. I then wrote a custom software application to draw a graph of the measured power versus range, where at each range the displayed power value is a looping playback of the spectrum recorded at that range. The idea was to kind of make a live graph as though there were, say, like 100 spectrum analyzers all operating at the same time on the range, and each placed a meter apart, so we could see how the power varied with range. And also, it could be compared with the predicted power level. And we'd see, how much variation there is at every point in the test range. Just to be perfectly clear, on the left panel, the power versus range graph, there's a range sample line, which is controlled by the slider on the bottom. And as I move the slider, and as I change the range sample line position, the spectral display on the right side shows the spectrum measured at that range. Now, I've never seen software like this before, but to me, I can't think of a better way of really getting a handle on what's happening spectrally on a test range.